this computer. And then let me also start making a list here. All right, so chapter 28, number 21. And let me just roughly do some timestamps here. I should keep meaning to grab my stopwatch when I'm at school in the lab at the campus doing the lab videos. But I'm just going to call this the beginning, and we'll call it 10:04. That way I'll at least have some kind of close to the timestamp. All right. So great. All right. So yes, I will do this one. All right. So chapter 28, or chapter 28, number 21. Let me switch over to the textbook here for a second. Oh, that's kind of small. Let me make that 100%, much better. All right, number 21. Let me scroll up here and take a look here at number 21. Consider the circuit as shown. What are the expected readings of an ideal ammeter and an ideal voltmeter? Good. Okay, let me start working on this by switching my screen to sharing. Actually, wrong button there. Try that one. There's my phone. Share. And oh yeah, I got to do the Bluetooth here on the phone. Alrighty, that should pop up in a second here. Keep coming. Nice. Okay, so tilt my phone a little bit. Looks like my holder's not as sturdy as it used to be. I'm going to have to get some pliers and tighten that nut down. All right. Okay, so number 21, the circuit diagram looks like this. And let me just, in case anybody wants to scan the video pretty quickly, I'll put chapter 28, number 21. Maybe I'll even put a page 1. This may take 2 pages here. And we have 2 batteries. We have a 6 volts and a 4.5 volt. That battery wants to send current through a 10 ohm resistor. And this other battery, the 4.5 volt, wants to send it to a 5 ohm resistor. Of course, that really means when they're connected here, they kind of fight with each other. So the stronger one may win, although the stronger one is being impeded by a bigger resistance. So a little difficult to tell. But in addition to that, both of them then want to send their currents through a resistor top and bottom that is made out of 6 ohms on each side. And I think that's everything. Now, the question then is, and I don't know if a different color would be useful. Oh, yeah, I finally ordered my pens. I kept thinking I was going to get some colored pens, and I finally realized I'm never going to make it down to CVS. And so I ordered through Amazon, but I still haven't got them yet. Anyways, but I got my red and my blue and my black here. So there is a voltmeter and there is an ammeter. Okay. Now, I think the easier one is the voltmeter, because what a voltmeter does is it measures the voltage difference between those two. All right. So in some kind of a weird sense, you could call this a loop, because we know that the sum of the voltages around a loop are equal to 0. Kirchhoff's, actually, let me switch this back to the chat so I can see if you guys are shooting anything at me. Exit full screen, there we go. And I can recall who asked it. So this was Andrew. Okay. So the voltage would just add up to 0 if I went around this small loop. So why don't I do this? I will start down in this bottom corner of the voltmeter, call it point A, this point B, this point C, and this point D. And so as I add up a loop, so I'll just go loop A, B, C, D. I'll start at A, and as I move, and if you can, the kind of the mental picture I like to give students is, if you were microscopically small and inside of the wire, and if you guys had the luxury of ever watching the Magic School Bus when you were little, the Magic School Bus, would do really neat tricks like this. You would get on the bus with Mrs. The Frizzle? Yeah, I think Frizzle. And you jump on
Netflix just put it back out on back out, so all 4 seasons are there.
Oh, cool. But you got on this Magic School Bus, and you could do things that you couldn't normally do on a school bus, on a normal field trip. And one of those episodes is they shrink down and they get in the wires, and that's kind of what I'm imagining here. I'm shrinking down, I'm getting in the wire, and so as I move through this wire, there's going to be a change in energy, and so it would be a change of 4.5, and it's a decrease in energy, because this is what we mean by the larger bar and the smaller bar. So from A to B, there's a decrease of 4.5 volts. And if I continue on through the wire, there is no change in energy in the wire. So B to C, there's nothing to worry about. So I won't write anything in my equation. And then from C to D, there's a change of 6. So I'll put 6, and it's an increase. And I know it's an increase because I go from the small to the big. And I get to D. And then finally, the last step would be what we're looking for. And that is then the voltage from, and I'll write it as D, minus the voltage at A, or maybe I'll just write it as VDA. But that would be the reading on the voltmeter, and I would get back where I started, and that's 0. So the voltmeter is really giving me a measurement of how much is the voltage at D greater than A. And so you can see here, depending on how this is set up, that this would be a 1.5, this would be D to A, I'll just put a 0, and so the voltage from D to A, or at least the absolute value, would be 1.5. Because there's not sure how best to say that. But as you would go from D to A, you must go down. And so I left it, the voltage from moving from D to A would be a decrease of 1.5. But the reading on the voltmeter is really saying how much is D greater than A. So I probably, depending on what you mean by this notation, probably picked a poor notation. But the point is, the reading on the voltmeter would be 1.5 volts, or it would be negative 1.5 volts. It really depends on which wire you put on there. In fact, I'm going to go back to the question, because I guess the answer I'm trying to point out here is D from A would be a decrease of 1.5 volts. That's what my loop equation did. And so if the voltmeter looked like this, if the voltmeter had the red connection going to D and the black connection going to A, what the voltmeter does is it takes the energy on the red wire, which would be D, and subtracts it from the energy at the black wire. And so this is saying D is greater than A by 1.5. So if you hooked up the voltmeter this way, you would get a reading of plus 1.5. On the other hand, if you hooked up the voltmeter with the black wire going to D and the red wire going to A, again, the way a voltmeter works is it takes the energy of the red wire and subtracts it from the energy of the black wire. So in this case, since we use the black wire at a higher energy, you would get a negative number. So then you would read a negative 1.5. So I need to go back to the question to decide if this is going to read a positive 1.5 or a negative 1.5, because it depends which wire we connect which way. But we're definitely going to have a 1.5. So if our concern is just what is the voltage, and we already know D is greater than A, then we can just say, oh, it's going to be 1.5. And I switch back here to my textbook. What does it say here? It says, what is the expected reading of an ideal ammeter and an ideal voltmeter? And they don't give me any indication on whether they're connecting the red wire to which one. So I'm going to go with an answer just 1.5, meaning that they're probably just asking, what is that voltage difference? But sadly, that doesn't really completely answer the question of which one is higher. But hopefully I did answer it for you, that this point D is higher than point A. And so the reading on the voltmeter is definitely going to be a 1.5 or a negative 1.5. And if you hook it this way, it's a 1.5. And if you hook it this way, it's a negative 1.5. And I know for me, a lot of times with the voltmeter, I won't care what plus or minus. And so I pay no attention sometimes to the red or black wire. It's just, okay, look it up. I want to know, I already know which one's bigger. I can tell by the battery that D is bigger than A. So I don't care about that. I just want to know what the numerical value is. And so there's sometimes in fact, I was running into this trouble yesterday. My son called me. His motorcycle broke down, and the way he described it, I thought it was his alternator. And so I drove out to Carp and started tinkering with it. And I go, well, this is not your alternator. This is something weird is going on here. And anyways, and in our troubleshooting, I got out my voltmeter and just poking around and didn't really care whether the red or the black one went to which one. It didn't matter. I was just looking for, did it have voltage? And so, I go, oh, this has the 13.2 volts. This is good. This one doesn't, blah, 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 blah. And finally troubleshooted it. But anyways, that's just my own story of just saying, just didn't matter which one was the ground and which one was hot. It was just, absolute value. All right. Well, I probably talked too much about that one because that one is probably the easier of the two. And so I like this red ink, but it kind of bleeds through. So I'm going to put the piece of paper between each layer here. Okay. So moving on and maybe putting my circuit diagram here on the screen so you guys can see it. Let's do the next one, which is the ammeter. And of course, the ammeter, by implying by its name, it reads how many amps, it reads how much current is going to be flowing through here. Let me go back to Zoom on this computer. All right. So here we've got to figure out how much current goes through here. And there's a lot of different ways of doing this problem. One thing, though, that is the main lesson here is you cannot complete this problem with just equivalencies. You could not narrow this down to just series and parallels. We're going to have to do a system of equations. Now, we can do a little bit if you want. It's maybe worth it, maybe not worth it, kind of your call. But the 6 up here and the 6 down here are actually in parallel with each other. It might be a little bit hard to notice, but if you, and here's kind of the way I like to test it, is I like to say, where there's a wire, the voltage is all the same. And so in this blue pen, if I kind of color in everywhere here that there is the wires, that would all have the same voltage. And maybe if I switch to a black marker and kind of color in the wires here, I would say it doesn't look much different on the screen. But that's supposed to be black and then it's supposed to be blue. But those would be the same. And what I'm getting at then is we can see that the two sixes are actually in parallel with each other. This voltage here in blue and this voltage here in black. The difference between the blue and the black here on this 6 and the blue and the black here on this 6 are the same, and hence they're in parallel. But notice I would not say that the 10 or the 5 are parallel. That's very tempting, and just don't do it. And that's a lesson to learn, because this right here would change it by 6 volts. And so the voltage from this blue to the other side of the 10 is not the same as from this side, the blue side of the 6, to the black side of the 6. This has changed a little bit. So we would not say that the 10 is in parallel with the 6. And then likewise, same thing about the 5. It changes by 4.5 here. So it does not have the same voltage as this 6 or this 6. And it also doesn't have the same voltage across it as this 10. So the 5 and the 10 are not in parallel with each other, and they're not in parallel with either of the 6. The only thing that's somewhat close to being an equivalent circuit here is that the 6 is parallel with the other 6. So if you wanted to do a little simplification, but I'm going to end up using my calculus and solving a matrix equation anyways. If I simplify this a little bit, I'll get a 3x3 matrix. If I don't, then I get a 4x4 matrix. Either way, I'm going to have my calculator do most of the work. So I don't necessarily think that this next step is that much of an advantage, but I will. And so I'm going to go ahead and replace and make an equivalent. So this will be the 6-volt battery. Down here will be the 4.5-volt battery. And I'll still leave the 10 and the 5 alone. But the two 6s I'm going to put together, and they're going to come out to be a 3. I suppose I should do some math on that, but remember they're in parallel. So 1/6 plus 1/6 would equal to 1 over the equivalent. And of course, a 6 plus a 6 is 2 6, which reduces to 1/3. So when you flip it over, you get the equivalency of a 3. All right, so if I do a little bit of equivalency, I get a 3. Of course, maybe the other bad thing about even doing an equivalency is right here. They don't want to know what current goes through the equivalent of these two. They want to know what goes through just this top one. Although, when I get to the end, I'm going to make this argument that this 3 is the equivalent of those two together. And if you look at them, since they're both 6, the current across the top and across the bottom would be the same. So whatever I solve for my 3, if I cut it in half, is going to be what's going through the 6. So that's kind of my long-term thought on that. That I'll just say, okay, it's going to be half of this. But I think you probably feel a little more comfortable with 3 equations, 3 unknowns, than you do with 4 equations, 4 unknowns. So that's why I thought, well, I'll go ahead and do that one equivalent step here. But this, again, gets me to, I think, a main lesson of this chapter, because we've been doing equivalencies first with the capacitors in chapter 26, and now you saw it first at the beginning of this chapter in 28, but at the second half of this chapter, you guys were being introduced to circuits that are a little bit harder and saying, look, not everything is quite as simple as just a series or a parallel. So you can't just break it down into series and parallel. When you run into that, you just got to go back to the fundamental physics of conservation of energy, and that's what Kirchhoff's loops rules are. So if we do the following, if we say that the current coming out of this 6-volt battery going this way, I'll just call it current number 1, and the current coming out of the 4.5 is current number 2, then it kind of looks like that's going to kind of group together and go through this 3. So I'll kind of arc it around the 3. Let me call that current number 3. And so I have 3 branches and therefore 3 currents. Okay. And I don't know if this came across in the lecture. I'll repeat it now. But of course, now those 3 currents, those are the 3 unknowns. And so I need 3 equations to solve 3 unknowns. But to be a little more clear, I need 3 independent equations. And if you remember, one of our laws, the Kirchhoff's laws, are the loop rule. Now, the loop rule means that we can do a loop. The one warning I have for you guys is you can't solve a problem by doing nothing but loops. You could argue that there are 3 loops here. And there is what I would call a top loop, a bottom loop, and then the big overall loop. However, the big overall loop is nothing more than the sum of the top and the bottom of the loops. So it's not an independent equation. So I like to say this, just do small loops only. If you do that all the time and only, you know you will have independent equations. Now, sometimes I got to admit the math is not the easiest that way. So sometimes I will pick a big loop and not the bottom loop or not the top loop. But I do know this, that I can only do 2 loops to get 2 independent equations. And so I'll have to go to Kirchhoff's current law, the second one, in order to get my 3rd equation. All right, so here's what I'm going to do, is I'm going to label some points here. I'm going to do the top loop first. I'll call this A. I'll call this point B. I'll call this point C. I'll call that point D. And I'll go ahead and do the top loop, which is the loop A, B, C, and D. And so if we add up all the voltages, we know that that has to come out to be 0. All right, so let's go from A to B. So as I imagine myself in my little magic school bus going from A, first thing I would do is go through a battery. That would be a change of 6 volts, and I'd put a plus sign because I went from small to big. Then there would be a change of voltage because of the resistor. And the Ohm's law from chapter 27, it would be the current times the resistance. So the current I'm labeling is I1 and the resistance is 10. The other piece to this is, would it be a plus or would it be a minus? And the answer here is it's a minus because you're going with the current. And as a side note, let me point out, notice I did not even ask what direction the current was when I was figuring out the voltage on a battery. The voltage on a battery is determined by the little and the big bar. It is irrespective of what the current is doing. But for the resistor, it depends which way the current is. So the current is going, in my picture, my chosen picture, to the left. And so in my movement from A to B, I'm going with the current. And you can imagine yourself, like I said, in Frizzle's class, and you're in that wire moving along. All right. So that gets me to point B. From B to C, there's nothing of interest. There is no, it's just a wire. There's no change in voltage. Okay, so keep going. From C to D, there's another resistor. So it would be the current, which we call I3, times the resistance, which is 3. So there's Ohm's law. And then the question is it a plus or is it a minus? Okay, well, as I go through this way, I look that I'm going with the current in my labeled picture. So again, that's a minus. We always want to look at the direction of the current to determine whether the voltage change is a plus or a minus. And that gives me all the way back to A. Again, nothing between D and A. And so my first equation, I guess, looks like this, if I simplify it a little bit. This is a 6. This is minus 10I1. This is minus 3I3. Okay. Let me do the bottom loop. Okay. So for the bottom loop, why don't I, let's see, call this over here point E and F. So I'll just go A to B to E to F and do the same type of logic. It's a conservation of energy logic. All right, so I'll add up the voltages around this loop. Okay, so going from A to B, and it's really the same thing we just did there, but I'll say it again. We would be moving through the battery. So that's a change of 6, and I know it's an increase because I go from the little bar to the big bar, and I'll say it again. When we look at the change of voltage in a battery, we pay no attention to the direction of the current. It's what the potential is determined by the chemical reaction, which is labeled with these big bar and little bar, okay? Then there's the change of potential here, which would be Ohm's law, so it would be the current times the resistance, so IR. And then the question is, are we going with the current or against the current? Are we going downhill or uphill? And the analogy I like to give in the lecture was, this is kind of like water. It's hard to imagine yourself getting in a wire and riding in a wire, but I think it's easy to imagine yourself in a creek bed, and this is water. And if you're in a creek and you're walking through the creek and you're walking in the same direction that the creek is flowing, the water is flowing, you would say, I'm going downhill. All right. And so I'm going downhill. I'm going with the flow. All right, so that's the A to B, and it's no different than these first two steps in this loop. There's where it gets different. So from B to E, no change there, okay. Then from E to F, we've got two elements here. The first one is a resistor, so it would be the current I2, and it would be the resistance of 5. So there's Ohm's law. That's the magnitude of it. And then now the question about plus or minus. And I would put a plus. You put a plus when you're going against the current. And so as I'm going from E and I'm moving through this little tiny wire, this would be like walking in a creek. And if you were in a creek, and as you walk through the creek, if you were going against the flow of the water, against the flow of the current, you would know you were going uphill because, the water flows downhill. Okay. So I would put a plus there. Then I get to this battery, which definitely has a voltage of 4.5. But again, the question is it a plus or is it a minus? And again, for batteries, pay no attention to what direction the current is, just big bar to little bar. That means from high to low. So we went from high to low. We went down. So we would go down. Then once we're at F, we go back to A to finish the loop. There's nothing more to complete. And so all of this has to equal to 0. And so if I simplify this equation, I can put the 6 together with the negative 4.5 and make 1.5. Then I would have a minus 10I1 and a plus 5I2. So I don't lose track of these. I'm going to put a little circle around them, maybe call this equation 1, and a little circle around this and call this equation 2. So we're on the road to what I hope is a answer to how am I going to get my 3 equations to solve for the 3 unknowns? Again, the 3 unknowns being current 1, current 2, and current 3. So I have 2 of them, and that's what I was saying. I do the loops first, and I always do the small loops unless I have a reason maybe to kind of switch it up, because I always know that the small loops always give me independent equations, and usually the small ones give me also the smallest equation. So I like the small loops. And so that's my recommendation here, is that you do the small loops. Now, you will never get enough equations just doing small loops. which is why you'll be tempted to maybe do a bigger loop, but that's not an independent equation, so that won't help you. All right, so you have to go to Kirchhoff's current law. Okay, and so let's do that. The node law, it's sometimes called, or the conservation of charge one. Let's look at point B for a moment. What's coming in is current number one, but also what's coming in number two. You might have to follow it a little bit, but number two is labeled down here through this 5 ohm resistor, but it would go to this point E and would have no place to go but to make the bend and continue on to B. So I can kind of label that would be current number two coming into B. And then, of course, likewise with number three. Number three, we said this was the current going, through this resistor here. But of course, it's coming from point C, and to come from point C, it must have come back here from point B. So coming out of point B must be current number three. So as we look carefully at point number B, and again, you can think of this as water, is we've got two streams flowing in, merging together and flowing out. And the stuff that goes in is equal to the stuff that goes out. This is this conservation of charge. So I like to, put it this way, that the sum of the currents in have to equal the sum of the currents out. If those didn't agree, then something weird would be going on, like the electrons would be just disappearing or something. And that would violate our conservation of charge here. Again, it's no different than water. If you have two streams flowing together and then merging, that the resulting stream, that is the merger of these two, the flow rate in that one is equal to the sum of the two coming in. Otherwise, the water's got to go somewhere. Water's like disappearing. And if you don't have like something taking water out of the stream, or you don't have the water evaporating, or if you don't have the H2O molecules magically disappearing, that what goes in has to equal what comes out. All right, so this would be my third and final equation here. Current number one and number two added together must be number three. And so that I will label as equation number three. All right, so I have three equations, three unknowns, a lot of different ways we can do the math to solve these. I am going to show you, I think, the same thing I showed you in the video lecture, that why don't we just set up a matrix, do the technique, it's called the reduced row echelon form, use the power of our calculator. To be honest, something as small as two equations, two unknowns, it's not worth the time to get out the calculator. I can do that by hand. This one I could probably do by hand even quicker than setting up my calculator, but I'm gonna set it up because some of these you get like 4 equations, 4 unknowns, and you don't wanna do those by hand. And particularly I wanna show you guys that, again, my tests are about physics, not about mathematics. So if I can show you a quick way to solve the mathematics, then if you're on a test and you come up with 4 equations, 4 unknowns, to you it doesn't really matter. 2 equations, 2 unknowns, 3 equations, 3 unknowns, 4 equations, 4 unknowns, 5 equations, 5 unknowns, 6 equations, 6 unknowns. The math is the same to you because you just put it into the calculator. Okay, so maybe a little review of some of the simple matrices that you've learned, not the real advanced stuff that some of you are learning now in 210, but just a simple matrix that if you maybe look at equation number 1, we could rewrite that as, we'll move the 10 to the other side, so it's plus 10 I1, 0 I2, and 3 I3. So when I move the 10 and the 3 to the other side, and then leave the 6, okay? And so that's just a rewrite of equation 1. Now, a rewrite of equation 2 would be 10 I1, move that over to plus, minus 5 I2. There is no I3s, and that would equal 1.5. So that would be equation number 2. And then equation number 3, I might write as 1I1 plus 1I2, and then moving this over would be minus I3 is equal to a 0. So there's just kind of a rewrite as I kind of dive into the math. But what this is nice for is you could write this in a matrix form. You'd start off with a 3 by 3 matrix where you put the coefficients. So there's the 10, there's the 0, there's the 3. There's the 10, there's the negative 5, and there's the 0. There's the 1, there's the 1, there's the negative 1. And if you take a 3 by 3 matrix and multiply it by a column matrix, and so a 3 by 1 matrix, which would be current 1, current 2, and current 3, if you multiply that out, you would get those 3 equations, right? Because this would, right here, you would go 10 times I1, 0 times I2, and 3 times I3. That'd be that first row. And the second row would be 10 times I1, negative 5 times I2, and 0 times I3. That would be the second row. And then the same thing would give you for the third row. So this matrix is just a convenient way of taking what was 3 equations and writing it as one matrix equation. Now let me make sure I complete the matrix, because we want this whole row to equal, and in this case it's 6, and in the second row it is a 1.5, and in the third row. So writing it out as a matrix is how we're going to solve this on the calculator, I think really easy, because I have, again, instead of trying to hand write out 3 equations, 3 unknowns, I'm going to use my calculator, because my calculator will do this. My calculator, by just a push of a button, will do all the mathematics that you probably learned in some math class. I'm not sure which one, but not as advanced as your 210. No, I'm not expecting you to use your 210, but it would manipulate the rows around. And if it manipulated it around to get a matrix that looked like this, a 1, 0, 0, 0, 1, 0, 0, 0, 1. Watch what this is saying. This first one, if you multiplied it out, would just say I1 equals. And the second one would just say I2 equals. And the third one would just say I3 equals. So in the process of manipulating this matrix to make it look like this is called the row reduction echelon form. Of course, as you know from mathematics, whatever you had to do, either by hand or with the calculator, to manipulate this matrix from here to here, every step that you do to the left-hand side, you have to do to the right-hand side. So there's going to be a bunch of manipulationing going on here. And so this would be A, B, and C. These would be different numbers. But if you look at this, then this A is the answer to what is current number 1. And this right here is the answer to what is current number 2. And this one right here then is the answer to what is current number 3. So that's how we're going to quickly get the answer with our calculator. We'll just let the calculator do whatever mathematics it wants to do. It might do the first and the third row combination. It might do first and second row combination. There's a lot of things. In fact, I first look at it, I would, if I was doing this by hand, I would do a subtraction between the first and the second row to get my new second row. I might even do a multiplication of the third row and subtraction of the second to get a new third row. Anyway, but all those mathematics I'm not going to do. And of course, doing that is a lot of handwork. Plus, you got to do it to the other side to get the answer. And fortunately, our calculator does that. So let me grab the calculator. And what am I using? I'm using the TI-84 and the 85. The 83. Well, not sure about the 85 and the 86. They're not very popular or common around, so I don't think too many people have those. You might have the 89 or you might have the Casio ones. Never really worked on those Casio ones, but the TIs is what most of you have. And let me just show you how to enter it on the TI anyways. And in my case, the TI 84. It's going to look like this on the calculator. We're going to set up a 3x4 matrix because it's going to be a 10, a 0, a 3, and then the reason it's 4 is because you need to put that in there. And so we like to kind of label this, if you've done any of these by hand, with a dotted line to say this may be our 3x4 matrix we're going to enter. But when you make the calculator do called a reduced row echelon form, it knows that, okay, this 3x3 is what's on this side of the equation. And so the calculator's got to reduce that to this part. And in the process, it'll perform the same operations on the other side of the equation and get some numbers here. So I'm going to get a 1 0 0 0 1 0 0 0 1, and as the calculator manipulates all of that, it will manipulate this to give me my 3 answers. All right, so that's why, kind of looking at this matrix, I'm going to come over here and go, okay, let me find the matrix. Now, I don't know if you can see, but my matrix button is under a second, and it's under the inverse key. So I'm going to go second and go to the matrix menu. All right, so when I go to the matrix menu, I'll just go to edit. And I can edit any of my matrices. You can see that in mine, I only have a matrix in slot number 1, and I seldom mess with more than one matrix, so I'll just do number 1 again. And the first thing it says is matrix A, and it has a 4x5. So it looks like the last time I was helping somebody with this, I must have been doing 4 equations with 4 unknowns, because the number of rows would be the number of equations you have. So I need to change that to a 3, enter, 4, enter. And so now I have a 3x4 matrix. And it looks like I've got some numbers already in there. I'll ignore those and just start typing in the new one. So the first one should be this 10 up here. So I'll go 10 and hit enter. When I do that, it just automatically moves to the next one. So 0, enter, 3, enter. And this last column was actually off the screen, and so it bumped over and scrolled my screen across, and so now I got a 6. And if you hit enter, it jumps down automatically down to this next one. So I'll just go 10, enter, -5, enter, 0, enter, and 1.5, enter. And now it jumps down to my third row, 1, enter, 1, enter, -1, enter, and then finally the last one, 0, enter. Well, it looks like it was already at 0. All right, and so maybe I'll just want to double check. That's the last row, move over, 3, 0, 1, okay, that's that one, move over to this one, 1, -5, 0, and then one more over, 10, 10, 1. Okay, so I've got my 3x4 matrix in there. And I'll just hit quit for a moment and just remember that that's in there. Because now here's the step of, okay, how do I get the calculator to perform this reduced row echelon form? Well, go back to your matrix menu. And you can see that the first one is the names, and the next one is the math you want the matrix to, the math to be done on the matrix. We went, of course, to the edit, so we could actually get, edit a matrix and make it a 3x4 and have the numbers we want. Now I'm going to go to the math. And if you scroll down the math, the first one says, hey, this will take the determinant of the matrix. Okay, this will be the transient of it. This will be the dimensions of it. And there's a bunch of things we can do with our matrix, but somewhere down here, there it is, under the category B is the RREF. And this says take the matrix and, you're going to perform this operation called an RREF. So you just hit enter. And of course, what you see on the screen is, okay, here's what you're asking the calculator to do, an RREF. It would be no different than if I hit the sine button, right? If I want to take the sine of 15 degrees, the first thing I do is hit the operation. What do I want it to do? I want to take sine, so I hit sine, and then I put in the 15 degrees. So here I want it to do the RREF, the RREF of matrix A. So now I have to go back to my matrix menu and select matrix A. There it is. And of course, you probably know with these TIs, you don't have to put a close, but I will for completeness. And so this is saying, take the reduced row echelon form of matrix A. All right, so I'll do that. Click. And there it is. So there's the matrix. There is the first part of it, the 3x3. As I said, it would give me a identity matrix, a 3x3 identity. That's this, what I was talking about, the 1, 0, 0, the 0, 1, 0, and the 0, 0, 1. And then these are the answers. Now, the decimal goes off the screen, so if you want to scroll all the way across to see the whole thing, fine, but just getting the first part would be fine. And so this would be a 363. This would be a 0.426. And this would be a 0.789. And so this is current number 1. This is current number 2. And you can see that adding those two together gives me current number 3. So that's how I would, solve for all the individual currents. Now I'm still not quite done with it. And I know I spent a long time here, but I thought maybe going through the Kirchhoff's loop rule, the physics of it, as well as the math of how I'm going to put this in my calculator would really be very helpful, especially that we got it on video, and I'm going to shoot that out to everybody a little bit later. But there's more to this problem. It's a longer problem than I thought it was going to be, because they want to know what is the reading on this ammeter. And what I have just solved is a equivalent circuit, not this circuit. And so I have the current in number 3 as 0.7, oh, I forgot what it was, 789. 789. Now I also have current number 1 and number 2. Maybe that was overkill. They weren't asking for those. But in terms of helping your education, I thought it would be good to see. So, all right. So then what I can do is come back here, and I made this argument at the beginning that I would argue here that this 3 is the equivalent of these two combined. And that since these are the same resistors, this being the total current would be split equal. And so the current through here would be half of what I just solved for here. Now I'll prove that to you before I take half. And so watch this. If I take a picture of 2 resistors that are in parallel and have the same resistance, and so I have a resistor, we'll call it R, and another resistor, call it R. A good name for this is a current divider because the current would come in. And so what I'm saying is these two together is an equivalent, which I'm calling current number 3. So current number 3 is what goes to this equivalent, which in our numbers is 3, because these were 6 and 6. And so if I just focus on number 3 and go from the equivalent circuit back to the real circuit comes in and splits here and here. So if I were to call this split, maybe current A and maybe current B, I do know this. The whole reason I put them together as in a parallel fashion is because they have the same voltage on them. So that means current A times the resistor, and maybe I'll just put the top one as resistor A, just in case we ever have a situation where the two in parallel aren't the same. In our problem, they are. They're both 6. But if I were to say that they're in parallel, that means they have the same voltage. And so using Ohm's law, current in the top one times its resistance and current in the bottom one times its resistance have to be equal. Now, in our case, resistor A and resistor B are the same. Now, that doesn't work. That doesn't happen in all cases. But for this problem, they are. And that's my conclusion, that the current that branches off into A and then the other half of it would branch off down to B, they would be equal. So that's how I'm going to finish this problem, by saying this equivalent circuit right here, where I just figured out how much went through number 3, in reality is coming up here and splitting. Half of it is going to this top branch, where it's the ammeter, and the other half is going to this bottom branch, where there is no ammeter, but if we had one, it would have the same reading as that ammeter. So the final step would to say the current in the ammeter would be the 0.789 cut in half. So 0.789 cut in half would be 395 amps. And my own curiosity and make sure I didn't mess up too badly in all those steps, let me call up the solutions to chapter 28. And again, this was problem number 21. And they got a current of 0.395. Great. And they got a voltage reading of 1.5. Great. Yay. Okay. So I hope I didn't bore you by taking too much time. I didn't think that would take nearly quite that much time, but it had really all the roots and the foundations of all the kind of advanced stuff we're doing in this chapter. All right, well, let me switch back to the chat room here. And Andrew, I hope that helped. I didn't turn off your mic and didn't see anything in the chat, so I'll move on here.
Yeah, it helped. Thank you.
Okay, good. Okay, so the second question up here from Anthony says, can you do number 22? I can, and let me write down a timestamp. So when I put together these videos, it's about 10:57 right now. And this will be chapter 28, number 22, okay? And maybe I'll just start with a new yellow sheet, put this under here, and then if anybody kind of scanning through the video sees, I'll put this first. So chapter 28, number 22, page 1. All right, let me switch back over to the textbook, and 22 is just the one below it. And they made loops with triangles. I hope that doesn't throw you off too much. Let me just draw the circuit. They'll start here with a battery. They give it a EMF of E. Now in the text, it says that this is 250 volts, okay? Down here, they label this as point A. They label this as point B. They then go through a resistor of R that they say is 1 kiloohm. So I'm going to just write it as 1,000. That gives us to point C. Going across from point C, because that's a node with 4 pieces coming into it. They have 2 R, which I'll also write as 2,000. And then they go to point D. Then they get to another battery, which has twice the voltage. So this would be 500 volts. And we get to point E. Then there is a resistor that is connected from C to E, and it's 3R. So 3R would be 3,000. Then there is a connection from C over to A, and that would be 4R, which would be 4,000. And then this one could be, it's supposed to be easy, but could be a little tricky. There's nothing really here. And so there'd be no voltage change from A to E. There's a connection though, so current can go through there, but there'd be no voltage change. All right, and then of course it says, determine the direction of the magnitude of the current in the horizontal wire between A and E. Yeah, so they're gonna kind of focus on that A to E. But before I get that far, let me just kind of do the same description that I mentioned. Now that I wrote that all down, let me come back to the Zoom on my other screen here. Okay. Yeah, okay. Let me just say the same thing, that you want to apply Kirchhoff's loop rules. I mean, if you can, if there's anything in series or parallel, fine. There isn't anything this time. You can see that, you know, as the current kind of flows here, it hits this node and goes in other directions. So none of these would be in series. And also none of them would be in parallel, because the parallel, you'd have to, you know, they'd have to connect both sides. And so maybe in blue ink, you'll notice that all 4 of these resistors are connected really essentially to the same voltage as C. And so they all have this voltage that I'll call the blue voltage, or the voltage at C. But the other side are, oh wait, I take that back. This is parallel. I wonder if I should put them in parallel. Part of me is saying no, because I want you to see how we could just jump into 4 equations and 4 unknowns. Could even, what would be better? But I'm afraid if I put them together, we kind of lose sight of our A to E, but that's not too bad, because then we can jump out of that. Let me not put them together, but they actually are in parallel. This black would all be connected together, and I didn't see that at first. So those 2 are actually in parallel. Now they're not in parallel with these guys, because again, the black would only come up to here, and then the voltage would change. So the voltage on the 1,000 from the blue to whatever would be not the same as the blue to the black. This would be blue to the black. That's why those two are in parallel, but this would be blue to whatever, but it's not part of the black again. So we, like the last problem, we could do a little bit of equivalency here, but it only gets us so far. The other ones can't. We got to go to Kirchhoff laws. So unless you care, I'll just go ahead and not do any equivalency on this one, since I did a little bit of equivalency on that one and then still ran into the same trouble we're going to do this one. Let me do no equivalency, and maybe that's better, maybe that's not. I thinking it's better, but we'll see here. So let's do some labeling. I guess the labeling, I would say, let's call the current that comes out of this 250 volt battery, and it comes out and it arcs around. Let me call that current number 1. Because it looks like then over here with this 500 volt battery, it's going to come out and arc around, and I'll call that current number 2. And so it looks like to me, they're going to come together here. And then, and again, a good analogy is like a set of water in a stream. It's kind of like two streams come together. They then mix at point C, and then they separate again. So the river comes together and then separates. But once they mix and re-separate, they don't have to re-separate in the same values. So in other words, this here, I better call it something different, I3. And this coming down here should be something different, which I'll call I4. But it would be a mistake to conclude that I4 is the same as I1. Now, it may look like it if you follow it down. You may say, well, doesn't I4 have to come around and go back into here? So then it has to become I1, so that would have to be I4. And say, well, no, because there is a current across this wire. And I'm not even sure which way it goes. It could go from over here at E over to A. And I'll label it that way and call it number 5. And if it did that, that would tell me that when it remixes, I3 was a little bit more than I2. So when it came back here, this I3 would kind of split off, and some of it would go this way, which I'm calling the I5, because a lower amount has to be going back to the I2. I know the I2 has to go back here. So again, if I3 was greater than I2 after they mixed, when it comes in, I know it would have to split that way. But it could be the other way around. It could be that I1 and I2 come together and they mix right here. And then as I4 goes down here, I4 is actually a little bit more than I1. And so when it comes here, it's at point A, and it gets here, this little extra part would have to go back that way. And so the I1 would go that way, and that's why we have to go this way. So I'm not real sure which way it goes, but I'll tell you what, I'll just then run through the math, and I'll just make a guess that it's the it goes this way. I really don't know. But if I am wrong, then when I go to solve my math, I will get a negative number for the I5. The I5 would be going the other way. And that's what we're looking for in this problem. What is I5? All right. So by not putting them together in any fashion, I really have 5 unknowns: current 1, current 2, current 3, current 4, and current 5. So as I was saying on the other problem, let's do the Kirchhoff loop one first. Note that there are 3 small loops. I would call this the left triangle. I'll call this the right triangle, and I'll call this the base triangle. But those are your 3 small loops. Now, they can be combined together, and you can make a loop out of the base triangle and the left triangle, or the base triangle and the right triangle, or the left and right. You could actually kind of make a loop. But I want to emphasize, those are not independent equations. So your best bet, I think the easiest bet, especially for the beginning student, is to realize that because there are 5 unknowns, you need 5 equations. And there are 3 small loops. So the first 3 of those 5 equations will come from these small loops. So let's do that. Let's take loop. What I'll start down here is A, and from A to B to C, and then back to A. My second loop would be maybe the base triangle. So from A to C to E, back to A. And so my third loop will be my right triangle. Why don't I start at C and go to D, C, D, go to E, and from E back to C. Okay. So those are my 3 small loops. Those are the first 3 of my 5 equations. So that means the other 2 equations I must get by Kirchhoff's second law, the conservation of charge law, because this is the conservation of energy. All right, so let's write these out. So from A to B to C back to A. So the sum of all the voltages would have to be 0. All right, so from A to B, there is a change of 250, and it's a plus because we go from the little to the big. Doesn't matter what way the current's going. In a battery, it's little to big. All right, so then I will go from B to C, and Ohm's law says the change would be the current, so there's I1 times the resistance of 1,000. The harder part of Ohm's law is it a plus or it's a minus? And I'll say it again, like the other problem. If you go with the current, so again, you got to imagine yourself in the wire. So we're back to that magic school bus problem. And so, and if you're, going with the current, so if you imagine yourself actually in a creek or a river and you are walking through it, you actually walk with the direction of the flow, you would be going downhill. So this must be a minus. So minus. Then I would get to C. And to finish this, I'd go from C to A. And again, this would be a current of I4 and a resistance of 4,000. So that's the change in voltage. That's Ohm's law, the current times the resistance. And again, is it a plus or is it a minus? It would be a minus because I'm going with the current. If I simplify this a little bit and call this my first equation, I could put the 1,000 I1 on this side of the equation, and I could put the 4,000 I4 also on this left-hand side of the equation and leave the 250 alone, and I would call that then the first of my 5 equations. All right. Now, if I do what you might visually look as the hardest loop, because it's got kind of this nothingness here, but this would be let's see, A to C. Okay, so the sum of all the voltages around this loop would be 0, and so I would have current 4. Current number 4, and then times 4,000. And then the question is it a plus or is it a minus? And in this case, when I'm going from A to C, it's a plus because I'm going against the current. When I get to C, from C to E, I would be going with the current. I'll put a minus. And then that would be a current of I3 and a resistance of 3,000. Then I would go here. Now here, I just go across the wire. There's no change in voltage. So there's nothing more to add. And doesn't even let current number I5 show up in my equation. That's kind of the weird thing about it. But nonetheless, I guess I would be done with this equation. I'll call it equation number 2 if I write it this way. And I'll just put it as a negative 3000 I3 plus a 4000 I4. That is what I'd call equation number 2. Okay. Then my third loop, same basic physics, the sum of the voltages would have to be 0. And let's say I'm going to start at C and go to D. So from C to D, it would be a current of I2, a resistance of 2000, and I'm going against the current. See, I labeled it as going this way. So against the current would be a plus. Then I would get from D to E. Now I'm at a battery. The voltage is on battery, real easy, just labeled 500, that's 500. But plus or minus, well, I go from big bar to little bar, so that would be a minus. Then I get to point E, and E to C would be then the current. So there is current 3, resistance of 3000. And I'm going against the current as I go from E to C. So that would be a plus. And if I kind of simplify this equation a little bit, I'll put the 500 over here to make it positive. And then this would be 2000 I2 plus 3000 I3, and I'll call that equation number 3. So there's my first 3 equations, and it has a current 1, a current 2, a current 3, and a current 4. So you might want to pay a little close attention to what's going to pan out here in just a second, because I technically have 5 unknowns. But if I had gotten lucky, and I haven't so far, had these 3 equations and there was only 3 of those 5 unknowns in them, I could actually then solve it right there for those 3 unknowns. That wouldn't be the full solution, but I could get those 3 unknowns. Now it turns out I didn't get lucky. I have 3 equations, but in these 3 I have 4 unknowns, not 5. See, that was kind of the weird thing about this 5 not showing up in this set of equations. So I might play a little game here to make my math a little bit easier. I'm not sure which is better, to have 5 equations with 5 unknowns or 4 equations with 4 unknowns. Well, it might be cleaner if I just give you 5 equations and 5 unknowns. So, okay, I'll do that. All right, so here is page number 1. Let me tear that off. But what that tells me is I still need 2 more equations that have to do with then the nodes. And so let me put the circuit back on the screen here, and I will look at point number C. See, point number C, if you, again, using conservation of charge, if you look at point number C, we've got current 1 flowing in and current 2 flowing in. They merge together and 3 and 4 flow out. So again, according to conservation of charge, the current going in must equal the currents going out. So that would mean current 1 plus current 2 would have to equal to current 3 plus current 4. And I would then call that equation number 4. Now at this point, I would say, depending on how you want to look at this, I might want to stop. Now, not completely stop, because the answer or the question wanted us to get number 5, but look at what I do have. Back here when I did the loops, I had 3 equations, and these 3 equations did not have all 5 unknowns in them. These 3 equations only had 4 unknowns. And so if you group equation number 4 with these 3, notice that this equation also does not have number 5. See, right now I have 4 equations and 4 unknowns. I could then solve for current 1, 2, 3, and 4. And I think I'll go ahead and do that. Maybe not quite yet, because here is really maybe the key and final step is to maybe look at point E and do the same thing, that the sum of all the currents going into point E, or maybe I should use a more formal word as node. So all the currents flowing into node E must equal to all the currents flowing out of that node. Okay, so if you look at this, what's flowing into node E is current number 3. What's flowing out, as we labeled, would be the 2 and the 5. And we have this option then of writing out a matrix with 5 equations and 5 unknowns, or we could just forget about this 5th one for a moment and have 4 equations, 4 unknowns. And then once we get that, we could just take current 3, subtract current 2, and realize that that's going to be number 5. So I don't know if you have a preference. Since 4 unknowns looks less daunting than 5, maybe I'll take that approach. So I'll go ahead and maybe just draw a line right here and say, let me not even look at equation number 5 yet. Let me just solve for current 1, 2, 3, and 4. All right, and then here's where I would encourage you to use the power of your calculator again and do this. All right, so let me write it in its matrix form. So maybe I'll do this a little faster than the last problem, since I was kind of explaining to all you guys how you set up the matrix. Let me do equation number 1 here. Let me give myself 4 rows, 1, 2, 3, 4, because this would be a 1,000, no current 2, no current 3, 4,000, and then this would be current 1, current 2, current 3, current 4, and that would have to then equal to 250. So that would be how to write equation, fold it over here. That's how I would write equation number 1 in a matrix form. 1,000 I1, 0 I2, 0 I3, 4,000 I4, all equals 250. So if I go to equation number 2 and write it in matrix form, I would have 0 for current 1, 0 for current 2, minus 3,000 for current number 3, that would be this times this, and then 4,000 times number 4. All of that would be then equal to 0. So that's in my matrix how I would write equation number 2. All right, how would I write number 3? Well, there is 0, current 1. There is 2,000, current 2. There is 3,000, current number 3. There is no current number 4, and all of that equals to 500. Okay, so there would be my 3rd equation. And then the 4th equation is right here on this sheet here. It says we have 1 for current 1, 1 for current 2. And I need to kind of put all these variables on the same side. So maybe if I won't actually rewrite it, but you can imagine I have to move that over. So that'd be a -3, -4, and then this would be equal to 0. So that would be my equation number 4. And as I said on the last problem, but I won't go into much more detail, if I enter this into my calculator as a 4 rows and 5 columns, the 5th column being here, and ask the calculator to do a reduced row echelon form, it's going to give me a 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. I won't see this part in my calculator, but it's kind of implied. And then I will have the answer A, B, C, and D. And we'll find out what those are in a second. But that would be then saying that whatever math is needed to manipulate this matrix, that manipulation is called the reduced row echelon form, then you would have to do it to this side of the equation. And that's why these numbers will change and become something. But the something they become is actually the answer. Because this right here is saying, you multiply this out, that current number 1 is equal to A. And this row is saying current number 2 is equal to B, and current number 3 is equal to C, and current number 4 is equal to D. That's why we like this reduced row echelon form, because whatever we did to get to this reduced row echelon form, we do it over here, and that gives us our answers, gives us our numbers we want. Okay, so I need to show you probably again how to get this into your calculator. All right. So maybe I'll zoom up again here, but the matrix here on mine is right there. It's in the blue, so I got to do the shift key to get there. So I guess I got to turn it on. And so I'll go back to the matrix. Maybe a little quicker than last time. I'll edit over and say, okay, I want to edit this matrix. And for better or worse, I always just keep doing matrix A. And so I'll hit enter. And the first thing it's going to do is ask me, well, what are your dimensions? What size do you want? And so now I have to have a little bigger matrix. It's a 4 by 5 matrix. So I'll just go 4, enter, 5, enter, and then I'll put my cursor down into the matrix itself. And then I can actually start entering then into my matrix. So my first value is 1,000. So I'll type 1,000 and hit enter. 0, enter. 0, enter. 4,000, enter. And 250, enter. So that's the 5 elements across the first row. And when I hit that last enter, it jumped down and started and scrolled back. And so I'm at the start of the second row now. So 0, enter. 0, enter. There's the negative 3,000. Now watch when I hit enter, because it's going to scroll over to column 4. And so I need to put in a positive 4,000. I hit enter again, it's going to scroll over to the 5th column. And I need to hit a 0. When I hit enter, it goes to the start of row 3. So 0, enter. 2,000, enter. 3,000, enter. 0, enter. 500, enter. And now the last row, 1, enter, 1, enter, negative 1, enter, negative 1, enter, 0, enter. Yay! All right. So there's the last row. Now, just to clear my head, I just like to say quit, so I can go back to the mathematical screen. Because what do I want to do, and it's still showing from our last problem, is I want to perform an operation. It's a special operation called an RREF, a reduced row echelon. And as I said, it's really no different than if I hit the sign key, because I want to do sign of some number. So I want to do a operation, an RREF of some matrix. So the first thing is to get the RREF, and then you can find that in the matrix window. And if you just go back to matrix and scroll over to the math and then scroll down, and it's something like the 12th one down or something, there it is. And so RREF, so you just hit enter, and then it just types it out there, RREF, and then open bracket. Then you go back to the matrix menu and select the matrix that you want. And in my case, it's the matrix A, so I'll select that one. And you don't have to close the bracket. The computer doesn't require that. But I always feel better when it's closed. It just looks weird, but it doesn't give you an error operation. That's probably good because it saves you a little time as you learn to use your calculator. All right, so here it goes. Here's the magical answer. Enter. Ding. All right, so there it is. There's the 4x4 identity matrix at first. And so the last piece here is my answer. So this is 0.01. 0.13, 0.08, and 0.06. So coming back to my original drawing of my circuits, guess what I have now is 1 and 2 are coming together. So 1 is going this way with actually really very little current. Most of what's going on is current number 2. So a 0.01 and a 0.13 come together and merge. So that's 0.14. And then they separate. And notice that the 2 separate into what's equivalent to 0.14. Now they don't separate equal. Looks like number 3 gets most of it. And 4 gets just part of it. That kind of makes sense because this is more resistant. So I would expect it to be harder, so less current would go that way than that way. That makes sense. But also notice that, number 3 did not split and become the same as number 2, which of course tells me then that as only 0.8 is coming down this direction, 5 has to be flowing this way to join up with it. So my labeling of number 5 is actually wrong. And so when I do a calculation for number 5, I'm going to get a negative number. Current really needs to come this way, right? Because remember, the 0.06 is coming down this way. And so when it gets down here to A, we only want 0.01 to go that way. So that means really 0.05 has to be going this way. And we can see the same thing here. If this is 0.08, but we've got to build it up to 0.13, we've got to have coming in this direction 0.05. So the 0.05 comes in this direction to E to merge up with the 0.08, combining together to get the 0.13. So clearly my current 5 must be a 0.05 going from A to E. But of course, we can just answer that back with the math that we did here. So if I put in current number 3, which is 0.08, and subtract off current number 2, 0.13, I will get a negative 0.05. So yep, sure enough, this last equation tells me that the current here has a magnitude of 0.05 and is flowing from A to E. And I should probably switch over here to the solutions. And oh, it looks like they jumped down to another page. And they say it is 50 milliamps from A to E. All right, well, fair enough. I have units of amps. So if I move the decimal 3, I would get 50 milliamps. Yeah, so 50 milliamps from A to E. So yeah, I get the same as the answer. Yay! Okay, good. All right, how'd that go? Let's see. We'll go back over to the chat room and see if there's anything for me. That help, Anthony?
Yeah, it did. Thank you very much.
All right. Good. Oh, hey, and it looks like it might be break time. Well, that's good. I'm getting kind of hungry. So there's no questions up there. Why don't I say let's take our break, and we'll come back at 12:30. At the time, yeah, 12:30. And I'll see everyone then. Bye now.